So it's the final lecture of this semester, and today we'll discuss something different. So today we talk about some algorithms, some problems which are actually solvable or not solvable, or solvable but it can be solved fast, and so on. So you may heard something like this problem is NP complete or something. This problem is NP hard, and usually it means that this problem is unsolvable. That's actually not exactly true. NP complete problem is not actually unsolvable problem. It's something. It has very specific meaning, and today we'll discuss what does it mean, and we'll discuss something more about problems, which problems are solvable, which are not. Why it is important? Because in practice, so when you have some real problem in your work, something like that, usually when you make a formal specification of your problem and you want to find some algorithm which solves your specific problem, in like 90% cases your problem will be NP complete or even unsolvable. That's kind of different, but we'll see. So usually it means that you need to change your problem to make it solvable, or you want to find not the exact solution, like exact minimum solution, or something like close to optimal solution, something like that. Let's go. First, we discussed a lot of problems in this course, and most of the problems have some time complexity. So usually time complexity, you may have something like say n log n time complexity, or let's say n cube time complexity, or something else. Again, this time complexity means that you need this number of operations to solve your problem. In complexity theory, usually all these problems are combined in a single complexity class, and this class is called P. P is the class of problems which are actually solvable in polynomial time. So if you can solve the problem in time complexity like n power of k for some k, then your problem belongs to this class P. Why we don't distinguish different time complexities? Why we put all these, like n cube and n log n is actually different time complexity, right? If you have n cube time complexity, it's much worse than if you have n log n time complexity. And if you have like n power 10, it's even worse. So if you have n power of 10 time complexity, it's pretty bad algorithm, but it will still be in the same time complexity class. The reason is that this property that the problem can be solved in polynomial time doesn't depend on the computational model you're working in. So usually we work in RAM model, right? So in RAM model you may have some time complexity. Let's say in RAM model you may have one time complexity. Let's say I don't know, n squared. And if you work on some different computational model, let's say pointer machine model, right? You may have some different time complexity because you don't have this arrays, and you cannot just make indexing in this arrays in constant time. So usually, yeah, you can simulate RAM model in pointer machine model just by adding the tree of all elements. So usually it's time complexity is greater than in RAM model by logarithm, or even the same. So it may be like n squared log n, just because you don't have this arrays and you need to build this tree to access all the elements of your array. But in some different computational model, you may have even worse time complexity. But still, this time complexity will be some polynomial of n. No, because you can simulate this RAM model in your computational model, and for each operation in RAM model, you will make up to some polynomial number of operation to simulate this one operation in RAM model. So this property that the problem can be solved in polynomial time doesn't depend on this computational model. So we will work in very simple computational model. So since we don't actually depend on the computational model, yeah, we will think about problem in very simple computational model. And one of the simplest computational models is Turing machine. So Turing machine is the following thing. You have, let's see, Turing machine. Turing machine works the following way. You have your data stored in like a single strip of elements. So you have this infinite strip of elements. And you can access only one element at a time. So you have like your current location, and you can access only this element of your strip. And your program is very simple. Your program works this following way. Your program is simply like automaton. So you have some states. Something like that. So at every time, at every moment, you have some current state. So this is the current state of your Turing machine. You look at your state, you look on the symbol in your current position, and you make something. So you do one of the following operations. So you look on your current state, you look on this at this character at this position, and you may change this character to some another character. You may move your head left or right, and you may change your current state. So basically, you have function. So you have your current state, and you have this value x here. And by looking on your current state and this value x, you decide what you do. So you move to some different state prime like this. You put some different value here, and you move your head left or right. So you move left, right, or stay in place. Also, you may hold. So you also may just hold. So you may just end your program. Very simple. So yeah. So this automaton simply explains what your program is doing when you look at this when it's looking on this data. So you have this data and this automaton, and that's all you have. Still, now this computational model is very simple, but it's still maintain this property. So if you can solve your problem in RAM model in some polynomial time, you also can solve the same problem in Turing machine in polynomial time. The polynomial will be different. No, because no, it's kind of complicated to do some. It's hard to make some complicated things in this Turing machine, yeah, because you can access only this element, and you have like fixed number of elements. For example, if you wanted to simulate like variable, like integer variable, then instead of having each cell containing single variable, you have only fixed number of elements, yeah. So you like make kind of bit representation of. You have this binary representation of your numbers. If you have local variable I in RAM machine model, then in Turing machine you need to have like binary representation of this I. And if in RAM model you make like +1, then in Turing machine you actually need to perform this +1 in the binary. So you go here, then find this 0, change this 0 to 1, and so on. Then next time when you want to add 1 to this number, you need to go here, find this bit is 1, so you go left, 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 find this 0, increase this 0 to 1, then go here, change all these 1s to 0s, and so on. So even this simple operation is kind of complicated in Turing machine model, but it's still polynomial. Yeah? So for example, +1 takes polynomial number of operations of the length of this number I. If you want to do something even harder, let's say if you want to find element in the array, so you have this, you have array A and variable I, let's say here. And you want to find value in array I with this index. So this is index in this array. And you want to find the corresponding value in array A. Then it's even harder than what you can do to find this value. You may put some special separator character here, then go back to I, make I minus 1, then move this separator one position to the right, then again decrease I by 1, and then again move it to the right, until this I becomes 0. When I is 0, it means your separator is in the position you need in your array A. So you move here, decrease, move here, decrease, move here, move here. The time complexity will be like n square, but it's still polynomial. So if every indexing in your array costs you n square time, then your total time complexity will be multiplied by this n square. But it will still be some polynomial of n. So this property that the problem is solvable in polynomial time is satisfied in this Turing machine. So even in Turing machine, you still can solve the same problem in polynomial time. So that's why we put all these problems in the same class. So this class doesn't depend, like specification of this class doesn't depend on the computational model. Cool. Nice. So we have this class P. So class P is a class of all problems solvable in polynomial time. And what people think next is there any problem outside of this class? So can we find any problem here which is not solvable in polynomial time? And it turns out there is some problem. The easiest problem which is outside of class P is the following problem. For example, you have a chessboard. So if you have chessboard n by n, and there are some chess pieces in this board. So let's say you have like queen here and some knight here. I'm not good in drawing, but you got the thing. So you have some pawn here and some king here. This is king. Okay. And so so you have some chess position in this large chessboard. So it's chessboard n by n. And you want to check who will win in this position. So you need to check who will win, whites or blacks. And it turns out it's impossible to solve this problem in polynomial time. It's hard to prove. Because again, it's easy to prove that problem is solvable in polynomial time. If you want to prove that problem is solvable, you just solve this problem. Easy, right? So you just solve this problem in polynomial time, and if you have solution of your problem in polynomial time, then your problem belongs to class P. For this problem, we actually need to prove that it's impossible to solve the problem in polynomial time. And to prove that problem is impossible to solve in polynomial time, we kind of need to check all possible solutions of this problem and just prove that all the solutions work slower than any polynomial time. It's much difficult, but people prove this. So people prove this that this actual problem is out of this class P. But we still can solve this problem, right? So no, because there is some fixed number of positions if you have board n by n. So the number of possible positions is just some finite number. So we can kind of brute force all possible positions on this chessboard and like build a graph of all these positions, see all the moves, and see who will win if we start from this position and so on. So this problem is actually solvable, but it can be solvable. Can be solved in polynomial time for any polynomial of n. So this problem is out of this class P, but it belongs to some class X. Let's see. X. Class X means that the problem can be solved in some exponential time. Exponential means, let me put it here. Exponential, that means that it can be solved in time, let's say, e in power of some n power k. So we make some exponent of some polynomial of n. Well, that's actually a big class. So anything which can be described as exponents of some polynomial may be put here. For example, n factorial. N factorial is, if you have n factorial, right? It's something like this. No? So n factorial also fits in this class, and so on. So everything which is not, basically anything which is not a polynomial fits in this class. Not everything, but quite a lot of things which are not polynomial fits in this class. There are problems outside of this class also. But usually everything you can, all the problem you can solve actually belongs to this class. Cool. Now, again, you're too quiet. Say something. Next, people start to explore the problems outside of this class. So, is there any problem here? And it turns there is a problem here. So there are problems which are outside of this X class. People go much further, and they find this class of all solvable problems. So let's build the class. It's called class R. From recursive, it doesn't. So it's historical name. So it's called class R. Class R is class of all solvable problems. So it's R is just solvable. What does it mean solvable? Solvable means that there is a solution for your problem, basically. Yeah. So if you have some problem, you can build a Turing machine which solves your problem. So if you give your Turing machine your input, it will produce your output in some finite number of operations. It's important. If your number of operations is infinite, then it means you don't have the result, right? Again, the important part is that Turing machine must stop at some point and give you the result. How do you prove this problem is outside of P? It is complicated. If you look at any proof about lower bound of some time complexities, all these proofs are very complicated. We learned some proof about, for example, sorting algorithms. So in one of the first lectures, we proved that it is impossible to sort the array faster than n log n time. It was very simple proof of the lower bound. Usually, when you want to prove something like that, so it's impossible to solve in polynomial time, you need to make something much more complicated. I'm not sure how this actually. I didn't read this proof, so I don't know how it proves. But I can imagine that this proof is kind of complicated. So all these proofs of lower bounds usually are much more complicated than proofs of the time complexity of the given algorithm. So if you're given the algorithm, you can prove the same complexity. Usually it's very simple. But if you don't have this algorithm, you just prove that this algorithm doesn't exist. It's much more complicated. And this asymmetry is actually quite interesting. We will find the similar asymmetry pretty soon. Now, let's move next. Next, when people discover this class of all solvable problems, people start to think, what is outside of this class? Is there any problem outside of this class? So is there any problem which is actually not solvable by any Turing machine? And it's actually Alan Turing was thinking about this. And he finds out that there actually is. There are problems which are outside of this solvable class. So there are problems which are theoretically not solvable by the Turing machine. And if your problem is not solved by Turing machine, it means it's not solvable by any standard computational model. So if it's not solvable by Turing machine, it means it's not solvable in your M model. It's not solvable in any other normal models, not quantum. Let's go. So how to find problem which is outside of this class? That's very simple. Let's go here. The simplest problem, which is outside of this solvable class, is the following problem. It's called hold problem. Hold problem is the following problem. You are given two values. You're given some program and some input. And you want to say if this program will hold on this input. So if you start your program and you give this program this input, will it stop in some finite number of operations or not? Will be stop on input x infinite time. So it's just Boolean function basically, yeah? So it's some simple Boolean function, you given it the program. No, you can describe program as just sequence of lines or something like that. So I given it a program and some input. And this function must say, will this program stop on this input at some point? Or if it will work infinitely, right? And it turns out this problem is unsolvable. Let's prove this problem is unsolvable. How to prove that some problem is unsolvable? Let's see. Let's think, if this problem is solvable, then we have this function. So we have some algorithm which is which takes these two things as an arguments and gives you the result, like Boolean value, true or false, right? So if you have this algorithm, then let's build the following thing. Let's build a very simple function. So let's build function f of parameter p. This program does the following. You give this program, you take one argument p, and you try to you call this hold with parameter p and p. Basically, you check if you give this program its code as an argument, will it stop or not? So you take this program and give this this sequence of lines is your program. Like every program is just sequence of lines, or you can interpret it sequence of bits or something. It doesn't matter. So program is a data, just block of data. If you give the same block of data as input to this exact program, will it stop or not? If this program will stop when given itself as an input, then we will do an infinite loop. While true pass, like in Python way. Okay, so it's just infinite loop. And if this program is not doesn't stop on this input, then we'll just return true. So if this problem is solvable, then we can build this function. Now let's think, what will happen if we give this function itself as an input? Let's see. What will happen inside this inside this function? So if this function returns yes, so if you're given this function f as an input and it returns yes, what does it mean? It means that if this function returns yes, it means that it will stop at some point. Yeah, and if it will stop, it means that hold function. So you give f and f as an arguments. This hold checks if function f stops when you give it function f as an input. It stops. So this hold returns true. You go inside this section and you have infinite cycle, infinite loop. Yeah. So if function f stops, then function f doesn't stop. It's contradiction, right? On the other hand, if this program f doesn't stop when you give it itself as an input, then this holds return true or return false. Then you go here and return true. So if your function doesn't stop, then it stops. Again, you have contradiction. So this program f cannot stop on this input and cannot work infinitely in this input. So you have contradiction in both cases. So it means that this program actually doesn't exist. So this program doesn't exist. It means that you cannot solve the whole problem. What would be the input of the input? No. You don't give it. So you just give this function as an input. Again, every function is just sequence of lines. Yeah. So you have sequence of lines of code. You just give this sequence of lines. So if you work in functional programming, that's not what you. So you don't give this function as a function. You give this function as a sequence of lines. So I give this sequence of lines to itself as an input. So I don't call it anything. I just give this function as a text, basically. So I give the text of this function to this function as an input. I can do it. Why not? Okay, so Alan Turing, in like middle of the last century, I'm not sure what's in 40s maybe. He found this proof, and it turns out there are some problems outside of this solvable class. What does it mean? What does it mean? First thing is that programming is complicated. When you try to solve some problem using when you want to find programming solution for your problem, it's actually unsolvable problem. Even analyzing the given problem, or the given program is unsolvable problem. So when someone gives you his program and asks you to analyze his program, it's actually unsolvable problem. So if you cannot analyze someone's program, that's not because you're bad, because it's problem unsolvable. So if you try to build something like code analyzer, for example, you build in some IDE like IGEA or C-Line or something like that, and you want to show the user that your program have bug here, it's actually unsolvable problem, because every analysis of the code is unsolvable problem. Even this simple problem, just to try to find out if your problem stops or not, is unsolvable. It means that all non-trivial properties of your problem actually are unsolvable. And if you can analyze your problem, it means usually that your problem is very simple. So if you have very simple problem, then you can find some heuristics to find if this problem is good or not. But if you have some real problem, usually it's that complicated that even finding some simple properties of your problem is unsolvable. That's sad, actually. No. From one side it's bad, from the other side it means that programming is actually a kind of cool profession, because you're actually solving unsolvable problems. Yeah. Next. Okay, forget about problems. Maybe the problem only with these programs. Maybe for some other objects it's not that bad. Maybe the problem is only when we try to analyze programs. Maybe we can analyze other objects better. It turns out there are a lot of objects which are that complicated that we cannot analyze them because they are as complicated as programs. For example, if you look on Conway Game of Life, yeah. So John Conway, so he built this game. It's a very simple game. So we have this infinite grid of cells. Every cell is dead or alive. So we have, for example, these cells are dead, these cells are alive. Something like that. And he makes some very simple rules. So when the cell became dead or it became alive, like this. So if the cell is dead and it has exactly 3 neighbors which are alive, so in the next step this cell becomes alive. And so it's exactly 3 neighbors. And if the cell is alive and the number of alive neighbors is less than 3 or more than 4, right? Then in the next step it will be dead. Like if it have on like these 2 neighbors, only 2 neighbors, then in the next step it will be dead. Less than 2, right? Less than 2. 2 is okay. Yeah. How do you analyze? In idea, you make the idea they implemented a lot of different heuristics, which analyze your specific code and find some very common bugs. So you know that usually programmers write code like this, and when you write code like this, then in this position you may have this problem. So it shows you the problems which are common for a lot of programmers. But it cannot analyze the code if the code is too complicated. If your code is too complicated, IDEA cannot show you any problems because it cannot understand what's going on here. Yeah, 2, 3, and 4 are good. Yeah, less than 2 and more than 4 are bad. Right? Right. Yeah, I see. And when he built this game, he found out that the behavior of this game is very interesting. So there are some, for example, there are some stable structures like this square of cells. So if you have these 4 cells, they form a stable structure. So every cell is alive. Every cell has 3 neighbors, so it stays alive. And all cells here have less than 3 neighbors, so they don't become alive. So if you have this square of 4 live cells, it will stay like this and will not change. There are some other objects. There are some, let's say, like this. If you have 3 cells, then in the next step, these 2 cells will die and these 2 cells will get alive. So in the next step, you will have position like this, and then back. So you have these like loops, and there are some much stranger objects. So there are some special structures which actually moves. So if you like build this structure and find what's going on, then after a few steps you have the same structure but shifted by some vector. So you have like moving structures, and there are some special structures which repeatedly create these moving structures and so on. So there are a lot of very interesting objects which can be built inside this game of life. What does it usually mean? Usually when you have something very interesting, it's unsolvable. That's like rule of thumb. This works like this. What does it mean? So let's look on the following problem. You're given some initial state of your game of life, and you want to check if at some point you come to some stable state. So if you start from this position in your game of life, will it stop at some point or not? Or will it grow infinitely or something like that? It turns out that all these problems are unsolvable. Why are they unsolvable? Well, basically because you can simulate the Turing machine using this game of life. So you can use these moving structures and stuff to simulate the Turing machine. And since Turing machine is unsolvable, then game of life is also unsolvable. You cannot check any properties of your position in game of life because if you can check any properties of this game of life, it means you can simulate the Turing machine and you can check properties of his Turing machine. And you can't check any properties of Turing machine because of this. That's actually very sad. So systems like this called Turing complete systems. So some systems are Turing complete. It means that you can simulate a Turing machine inside this system. And if system is Turing complete, it means you cannot check any properties of this system. Because if you can check these properties, you can check the same properties on Turing machine, and you cannot. Okay. So game of life is one of these Turing complete systems. Example project grows infinitely. It's large, and I cannot remember it. So it's not small system. There's a system which produces gliders one by one. So after a few steps, you have the same system plus glider, and this glider is moving. So yeah. I cannot build it from memory. So you can Google it. It's kind of fun stuff to Google. Okay, this is one of the example of Turing complete system, but there are a lot of Turing complete systems. Again, usually if you have very interesting system, usually it's NP complete. For example, one of the systems works like this. You have something like, so you have squares. Every square has some numbers on each side. So let's say you have 1, 1, 2, 1, and here we have 2, 2, 1, 1, and here we have 1, 2, 1, something like this. So you have a set of some squares. Every square has some digits on its sides. Well, usually it's colors, but I can use various different colors actually. So I have two colors. So usually it's like this. So every side has a color. Yeah. So this color 1, and this will be color 2. And now you can build figures of these squares, connecting them with sides of the same color. So you can take, for example, you can take this square and this square, and you have this square, 2, 2, 1, 1, and then here you have this square, 1, 1, 2, 2. And then here you can put another square, 2, 2, 1, 1, and here you put another square, and so on. So you can connect these squares by the sides of the same color. And what you want to check, for example, if it is possible to fill the entire space using only these squares. So if you have only these types of squares, is it possible to fill the entire plane using just these squares? And it turns out this problem is also unsolvable. Why it's unsolvable? No, basically it's because this plane is infinite. So in this infinite plane, there are infinite number of states. So basically what you can do is simulate your Turing machine using this system. Well, it's like this. So you have like every row of this tiling is state of your Turing machine, and when you move to the next row, you do something similar to the Turing machine. So you can simulate Turing machine using only these squares. So by giving this some set of types of squares, you can actually simulate the given Turing machine. That's it. Another simple example works like this. So it's another cell automaton. So Stephen Wolfram, it actually was not so long time ago. So it was in the 90s. He was exploring different automatons, not like this. So basically, it's like Game of Life, but one-dimensional. So if you look on something like this, but one-dimensional, so we have this again. We have this line of cells. Each cell is dead or alive, and you have some rules about each cell. So each cell looks at the two neighboring cells and find its next state. So the next state of this cell depends on its state and state of two neighboring cells of this cell. So basically, if you have this x, y, and z, then to create this automaton, you actually need to make a function. So you need to make this function from x, y, and z to the new value of y prime, like this. So we look on these three cells and find the next value of this cell. So this is the Boolean function of three variables. So there are at most 256 different functions. Yeah. So there are 256 different automatons in one dimension, right? So he tries to explore all these 256 automatons and check if there are some interesting automatons in this group. You can skip some symmetrical ones. So if this is symmetrical, you can skip one of them. Then there are a lot of non-interesting automatons which just die immediately. So you start them and they die, or you start them and they all become alive, or something like that. So when you get rid of all non-interesting automatons, there are some few number of automatons which actually do something interesting. One of these automatons works like this. You have very simple rules. For example, if cell is dead and the cell to the right is alive and something here, then this cell became alive. So if cell is dead and cell to the right is alive, then this cell became alive. And if this cell is alive and both neighboring cells are alive, then it became dead. Yeah, that's all. Very simple rules. And when he built this automaton, he actually started to run on different inputs, and he found out that the behavior of this automaton is very complicated. So if you start this automaton on some input, it usually makes something strange, and then sometimes it stops, sometimes it doesn't. So it does something strange. So he thinks if this automaton is Turing complete, and few years after they actually prove this simple automaton is Turing complete. It means you can simulate Turing machine using just this simple automaton. So you take your Turing machine, produce some input for this automaton, and this automaton will work as the Turing machine from which you started. What does it mean? It means that you actually cannot predict the behavior even of this simple automaton. So things are kind of strange in this way. So there are a lot of problems which are actually unsolvable. Usually when you have some interesting system, and in this system you can do something like Turing machine, so usually it happens when you have some infinite memory. For example, in this automaton, the length of this line is infinite. If you have limited number of memory, then your problem is actually solvable, because you can iterate on all possible states of your memory. But if your memory is infinite, usually it means your problem is not solvable. Not always, but most times. Okay, let's move next. So these are the complexity classes. So there are some problems here and some problems outside. Now, when you move to this direction, next thing you want to do is to move into this direction. So this problem is unsolvable. Okay. So this problem is solvable in exponential time. Okay. But what is between? What is here between this problem solvable in polynomial time and problems not solvable in polynomial time? Is there any special class between these two classes, which kind of problems which are solvable in polynomial time or not? Maybe something like that. And when you explore this region, you find the NP class. So between these two classes, there is a special class called NP. That's another interesting class. So usually when people think about NP class, they say that NP is non-polynomial. It's actually not. It's common misunderstanding. So if you hear that somebody talking about NP problems like non-solvable problems, it's not. And P class is actually closest possible class to P, something like that. So it's what's interesting about problems in class NP, we actually don't know if it is solvable in polynomial time or not. So if we find any problem in this NP class, we actually don't know if this problem belongs to P or not. Maybe all problems in P class are actually in P class. Maybe not. We don't know. Probably not. But who knows? What has been problem in NP class? Problem is in NP class when it can be solved in polynomial time by non-deterministic Turing machine. What does mean non-deterministic? Works in polynomial time by non-deterministic Turing machine. What does mean non-deterministic Turing machine? It means that this Turing machine have some advice from some how it's called. So at some point, your Turing machine may have some non-deterministic choice. So usually, what's going on? So you have this automaton. So you have state, and from each state you have a single transition to another state. Yeah? So you have. So if you stay here and you see character A, you move to this state. That's usually how it works in automatons, right? In non-deterministic Turing machine, you may have several different transitions. So if you see this character A, you may move to this state, or you may move to this state. And this transition is not deterministic. So when you stay here, you may go here, or you may go here. So you ask someone for help, and it tells you where to go. So it tells you to go here or to go here. Now, how to solve problems using non-deterministic Turing machine? Again, like a normal Turing machine, you have some. Let's say you have some special state. So the special state for answer yes, and another special state for answer no. So you run your Turing machine, and at some point you reach one of these states. So you go here or you go here. So if your Turing machine is here, it means the answer to your problem is yes. If you go here, it means the answer to your problem is no. Okay. Now, the person who helps you actually wants you to make the answer yes. So the person who helps you to find to choose between these two transitions actually wants you to go into this yes. So if it is possible to make any choices which force you to move into this state, then you will be in this state in the end. So the answer is yes if it is possible to reach the state yes if you make some deterministic choice. So again, at some point you make some non-deterministic choices and you reach this state yes if it is possible to reach the state yes. That's the meaning of non-deterministic Turing machine. Again, you may think about it. You may think of it like this: someone knows the answer. Yeah. So you're running your Turing machine. You don't know the answer, and someone knows you the answer. And the man who knows the answer actually tries to prove you that there is an answer. Something like that. So he knows the answer. He knows the answer is yes. So he shows you which transitions to take to move to this state yes. And if the state is no, if the answer is no, then it is impossible to reach state yes. So this man gives you some instructions, but it's actually impossible to reach the state. So you reach the state no. Yeah. Usually in complexity theory, we think only about problems with no yes answer. All these classes usually are about problems with yes or no. If you have some problem which you need to find find something, like find the optimal path, you can transform your problem to yes/no problem like this. So if you find the minimal answer, you may transform it to something like this. Is it possible to? You want to find minimal something, yeah? You can transform your problem to yes/no problem like this. So you can say like is the x such that f of x is less than d. So you're given this x and d, you're given this d, and you answer if it is possible to find the value of function less than d. And then by making binary search over this value d, you kind of find the minimal possible answer. Something like that. So all the problems in this theory are described as a yes/no problems. There are another classes which works this problems of like when you need to count something or something like that. So all these complexity classes are usually described as problems with yes/no solutions. Yeah. Something like that. Okay. What I was talking about? About non-deterministic machines. There is another way of thinking about non-deterministic machines. Non-deterministic machines. No, let's solve some problem. For example, one of known NP problem is problem of finding Hamiltonian path. So you have this graph. You have some graph, and you want to find the Hamiltonian path in this graph. No, not find. You want to check. You want to check if this graph contains a Hamiltonian path. Let's make cycle, for example. It's a little bit easier. So you're given some graph, and you want to check, is there a Hamiltonian cycle in this graph? For example, for this graph, the answer is yes. You can build cycle like this. You go here, 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 here. Yeah, this is a Hamiltonian path. So, how to build a non-symmetrical Turing machine? Very simple way. So you start from some point, and then each time you make some non-deterministic choice. So you ask someone, where should I go from this position? And if this someone knows the correct answer, it can show you where to move. So you're standing here, then you ask where to go. I can go here or I can go here. So you make this non-deterministic choice. And someone tells you go there. So you go in here. Now you're standing here. You have two possible. You can go here or you can go here. So again, someone just tell you to go here. Then you go here and so on. So at some point, if you have some advice from someone who knows the answer, you can actually build the correct answer. That's basically the meaning of the NP problems. Yeah, so NP problems are actually problems when, if you know the correct answer, you can prove someone that the answer is yes. So if you know that the answer is yes, you can actually provide some advice to this Turing machine to actually prove it that the answer is yes. Something like that. And if the answer is no, you actually can't provide any proof. Because if the answer, it's easy to prove that the graph contains Hamiltonian cycle. Yeah, you just show this Hamiltonian cycle and say this is Hamiltonian cycle, and you look and see, okay, this is Hamiltonian cycle, so this graph contains a Hamiltonian cycle. And if you have some graph which doesn't contain Hamiltonian cycle, you can't prove anyone that this graph doesn't contain a Hamiltonian cycle, right? No, because how you can prove someone this graph doesn't contain any Hamiltonian cycle? It's hard. So again, this is some asymmetry between something you can prove that the answer is yes, And you can prove the answer is no in polynomial time. Yeah, it's important thing about polynomial time. You can prove someone that the answer is yes in polynomial time. So if you're given the solution of your problem, you can check the solution is correct in polynomial time. This is usually called the certificate of the problem. So if you're given this certificate, like this cycle, you can check this certificate is correct in polynomial time. That's just another way of thinking about NP problems. So NP problem is the problem then the answer is yes. If and only if there is some certificate such that you're given this certificate to problem and it returns yes in polynomial time. NP complete is something different. So we're moving to NP completeness. We're pretty close. Now, if the problem belongs to P, it actually doesn't mean the problem is hard, because actually any problem in P actually belongs to NP. So class P is completely inside class NP, obviously. Yeah. If you can solve something in non-deterministic machine, Turing machine, you can solve the same. If you can solve something in standard Turing machine, you can solve the same problem in non-deterministic Turing machine. You just don't do any non-deterministic choices. So any Turing machine is actually non-deterministic Turing machine if you don't make any non-deterministic choices, right? So every problem inside P is actually inside NP. So if you prove that your problem is in NP, it actually doesn't mean this problem is hard. The problem is then your problem is NP complete. Yeah. So what does it mean? NP complete problems are the problems which kind of on border of this. So something like here. So there are some problems which can be proved to be on the border of this NP class. So it's the hardest possible problems in class NP. How to prove that the problem is hardest in the whole class? To make this proof, we actually need to think about how to prove that one problem is harder than another problem. So let's say you have two problems. Let's say problem A and B. And you want to prove that problem A is harder than problem B. Now, how can you prove this? Okay, so what does it mean problem A is harder than problem B? It means if you can solve problem A, then we can solve problem B as well. Okay, so problem A is harder than problem B if we can solve problem B if we solve problem A. You can think about it. So there are different definitions of reducing the problem. One of the way to reduce problem, it is usually making by reducing one problem to another problem. So you can reduce problem B to problem A. Let's do it like this. So how we can solve? We see if we want to solve problem B, yeah. Instead of solving problem B, we will solve problem A. But we cannot give just input of problem B, so we won't solve some B from X. So we want to give this input X to problem B and solve this problem B, right? So instead of this, we will modify this input and give this input to problem A. So we will run problem A on the input of problem B modified by this function f. And this f is calculated in polynomial time. Yeah. What does it mean? It means that if we can solve problem A, then how to solve problem B? We take the input of problem B, perform this modification and have the input for problem A, give this input to problem A, solve problem A, then the result of this problem A will be the same as the result of this problem B. Yeah, this polynomial time modification. Yes, this modification should be done in polynomial time. Then the whole thing will run in polynomial time, because we will make this modification in polynomial time and then run problem A in polynomial time. No, it will be a polynomial of some polynomial, so it still be some polynomial, right? So the whole thing works in some polynomial time. That's all. Now, for example, okay, let's make the same example. So for example, I know that finding a Hamiltonian cycle is NP, right? So let's prove that finding a Hamiltonian path is harder than, no, not easier. It's not harder. It's actually not easier. Hamiltonian path is actually not, let's say, not easier like this. It's not easier than Hamiltonian path. NP-hard and NP-complete. We'll talk about NP-hard and NP-complete problems in a few minutes. Let's build this example and then we'll go to NP-complete and NP-hard problems. Okay, that's kind of strange. Let's recycle. Let's prove that building Hamiltonian path is not easier than building Hamiltonian cycle. How to prove this? Imagine we know how to build Hamiltonian cycle. Hamiltonian path. Imagine we know how to build Hamiltonian path. Let's try to use this function to build the Hamiltonian cycle. So again, you have this graph. So you have some graph, and you want to find the Hamiltonian cycle, but you know how to build Hamiltonian path. So how to use this function to find Hamiltonian cycle? Well, you can do it like this. You can take any node of your graph, just double this node, like this. Just make two copies of the same node. Now your Hamiltonian cycle is actually a path. So if you look on your Hamiltonian cycle, like this. Now your cycle is splitted in this point, so you have this path. And now all you need is to find a Hamiltonian path which starts here and ends here. If you build path from here to here, which go across all the nodes of your graph, then you build this Hamiltonian cycle. And now you need something to force your Hamiltonian path to start here and to end here. And you can force this by adding just these two nodes. So you add two more nodes here. And now if in this graph you build a Hamiltonian path, it will be forced to start here and end here. So in this graph you build the Hamiltonian path. It will start here and end here. Now you remove these two edges, combine this start and this finish, and you have this Hamiltonian cycle. So if you know how to build Hamiltonian path, then you actually can use this function to build the Hamiltonian cycle. It means that building Hamiltonian path is not easier than building a Hamiltonian cycle. Okay. That's how to prove that one problem is not easier than another problem. And now the interesting part. There are some special problems. They're called NP-hard problems. NP-hard problems are known to be not easier than any problem in class NP. What does it mean? It means you actually can reduce any problem to your NP hard problem. And NP complete problem means that problem is NP hard and belongs to NP. It's wrong way. This way. Right. No. Sorry. This way, right? Yeah, this way. Okay. So NP complete problems are very special problems. These are problems which belongs to class NP, and they are not easier than any problem in class NP. It means we can reduce any problem in class NP to one of these NP complete problems. So if you take any problem in NP class, you can reduce it to your NP complete problem. What does it mean? It means if we solve any one of these NP complete problems in polynomial time, so if any NP complete problem belongs to class P, so if you solve any of NP complete problems in polynomial time, it immediately follows that NP actually equal to P. Well, because if you can solve any of these problems in polynomial time, it means that all problems in NP class can be solved in polynomial time. That's why people actually think that it's impossible. No, because if it is possible, it means that any problem. No, what does it mean? What does it mean if NP equals to P? It means that if you can check the solution in polynomial time, you actually can find the solution in polynomial time. It kind of looks strange. Yeah? It doesn't mean it's false. Maybe it's true. Nobody knows. But it's kind of strange because it means, again, what does it mean? It means that if you can check your certificate in polynomial time, then you can find the certificate in polynomial time. If you're going to do something this way, you can do something in the opposite way. If you can check, then you can produce. It's a strange thing, but nobody knows if it is true or false. Have enough time? Do we have enough time? Okay, we have enough time. Let's do something interesting. So how do people prove that some problem is NP complete? Wait, there is a list of problems known to be NP complete. One of the simplest NP complete problem is the following problem. Okay. So what is this? So one of the simplest NP complete problem is the Freestyle problem. In Freestyle problem, you have a formula in Freestyle form. So you have this formula looks like this. So you have this set of how it's called in English. So it looks like this. So you have number of brackets. In each bracket you have something like this. x1 or not x2 or x3, and in the next bracket you have something like x2 or x3 or not x4, and that's all. So in each bracket you have three elements. Each element is either the variable or negation of this variable. So you have this, like this. Clauses. Good. Thanks. My English is not that good. I actually forgot how to do it. So yeah, there are clauses. In each clause you have these three elements. Okay. Cool. Thanks. Now, this problem isn't NP complete. I will not show you that this problem isn't NP complete. It's kind of complicated. We'll talk about it. So if you want to know how to prove that some problem is NP complete, so the first problem, we can talk about it in a minute. But now I want to do another stuff. So there is a list of problems known to be NP-complete. So how to prove that your problem is NP-complete? To prove that your problem is NP-complete, you actually need to reduce one of NP-complete problems to your problem. Yeah. So this is the whole NP class. Okay? So this is your problem. You want to reduce all problems in NP to your problem. How to do it? The easiest way is to take one of the problems known to be NP-complete. So this is some known NP-complete problem. So you have, so there is a proof that any NP problem can be reduced to this problem. And now you reduce this problem to your problem, like this. And now any problem in class NP can be reduced to your problem. It means that your problem is NP-complete. That's the easiest way to prove that some problem is NP-complete. Just take some known NP-complete problem and reduce the problem to your problem. No one knows if P is equal to P not. So no one knows if it is true or not. Most probably not, but no one knows. No, basically every year there are some different proofs about the P versus NP. But usually all these proofs are not that interesting. So people actually investigate this part very deeply, and there are a lot of problems about proving this thing. So so people work around this problem quite a lot, and there are a lot of different difficulties which actually prevents you to prove this. And as we know from the Gödel theory, there are some problems in mathematics which actually are unprovable. So maybe this is one of these problems. No one knows. So if you know mathematical logic, there is always some problem which is there's always some, how it's called, I don't know. So there are always things in mathematics which cannot be proved. Yeah, so maybe it's one of these problems. Yes, and we actually cannot prove it is unprovable. Yeah, that's another problem of mathematics. In mathematics, you cannot prove that something is unprovable inside your theory. So it's complicated. So mathematics is complicated. Now let's go to something we can prove. What we can prove? We can prove that some problems are NP-complete. For example, let's prove that knapsack problem is NP-complete. So let's prove that knapsack is NP-complete. How to prove that knapsack problem is NP-complete? We will reduce Freestyle problem to knapsack problem. And since Freestyle is NP-complete, then knapsack is NP-complete. How to do this? The easiest way is to do the following. Let's solve the following knapsack problem. Simple, very simple knapsack problem. We have some weights. And we need to check if it is possible to combine some weights to have sum equal to S. With sum equal to S. So we're given some set of elements, and you want to find some subset such that the sum of this subset equals to S. This is just a very simple version of knapsack problem, right? And even this problem is NP-complete. Let's prove this. How to prove the problem is NP-complete? Again, to prove this problem is NP-complete, we need to take Freestyle problem and reduce this problem to your problem. So we take this formula, and from this formula produce some set of elements and some number S, such that if it is possible to get some S only if it is possible to solve this formula. So if there is if there are some values of these variables which satisfy this formula, if and only if you have the subset with sum equal to S. Well, how to do it? No, easiest way to do it like this. Let's take this formula. Let's take all the clause. Let's take all the variables. For each variable, we create two elements. So let's create variable for x1 and not x1. So each variable of this formula will produce two elements for the knapsack problem. One for x1, another for not x1. One for x2, another for not x2, and so on. So each variable will produce two elements for your knapsack. What will be the weights of these elements? Well, let's see. So we will look on each variable and see in which clauses it actually appears. So for example, this x1 appears in this first clause. Let's have one more. Let's have one more clause. Let's see. Let's say not x1 or x2 or not x3, something like this. So we look on the first variable. First variable appears here and here. So in this first element, we will make the first digit equal to 1. All other digits equals to 0. And here we have not x1. So we will put 1 in this position, and all other positions will be 0. So the digit representation of each weight will be the following. We'll put zeros in positions where the clause doesn't contain this variable, and we put 1 in positions when the clause contains this variable. x2. We have x2 here and here, so it will be 0, 1, and 1. Yeah. Again, we have 1 here because we have x2 here, and we have 1 here because we have x2 here. Not x2 we have here and all. Yeah. So we have 1, 0, 0. And so on. So for each variable we create two elements. Each element have ones in positions when we have this variable in the clause. That's all. So now, when we will calculate the sum of elements, the sum of elements will represent the state of the variables in this formula. So let's look on the state of variables in this formula. If we take some values for each variable, we will pick one of these elements. So we need to pick one of these elements, one of these elements, one of these elements, and so on. So for example, if you take x1 equal to true and x2 equal to false. Then you will calculate the sum of these elements, and the sum will be 1, 1, 1. But it's not always like this. For example, if you have x3 here, if you have this x3, which is 1, 1, 0, and you pick x3 equal to true, yeah, then here you will have like 2, 2, and 1. Again, what does it mean? It means that you pick two variables in the first clause, two variables in the second clause, and one variable in the third clause. Yeah. So this is true. This is true. Here you have this is true. This is true, and here you have this is true. So each digit means the number of variables which satisfied in each clause. Right? Now, what we need to do is to force our knapsack to use only one variable from each group. So we need to somehow force our knapsack to take only one of these items, only one of these items, only one of these items, and so on. So for each this pair of items, we can pick only one of them. How to force a knapsack to do this? Very simple way. We will add more digits. No, so these digits represent clauses. Yeah. So we will add more digits here. Now, these digits will prevent us to use two items of the same type. So how to prevent our knapsack to use these two items at the same time? We'll just pick another digit and put one here. For these two elements, we'll put one in this position. For these elements, we'll put ones in this position. So. Now, if you take one of these elements in each pair, then here you will have 1, 1, and 1, and so on. We should use base n representation. No, we can use base 10 representation is enough. Base 10 will be enough. That's all. No, by now each element is 1, 2, or 3. So base 10 will be enough. That's all. Now, again, if you look at any solution of your Boolean formula and try to build the same solution for your knapsack problem, you do the following. So from each one of these two items, you can pick only one item because you want in the end to have these ones. So if you pick two items of the same type, you will have two in this position, and you need to have one in this position. So you can pick only one item from each pair. Now here, you pick some items. So in the end, you will have some digits here, and this distance shouldn't be 0. So these digits are 1, 2, and 3. That's not exactly what we want to do. We want this sum to be exactly S. Yeah? So we cannot make 3 possible values for each digit. We need to have only 1 possible value for each digit. So we will add some more bits. So for each position, we will add 2 more special elements. These special elements will force each digit to be exactly 3. So we'll add, for each clause, add 2 more variables with 1 in this position. Good enough. Yeah, let me put the whole picture here. So you have these, so this x1, not x1, not x1, x2, not x2, and so on, xm, not xm. So you have this part when you have ones in positions when you have these elements. So this is the interesting part. Now here you have ones in these positions, like this. And also you have these additional elements just to make all the digits equal to 3. So you have another 2 ones here, another 2 ones here. Special elements. So now you give all these elements to your knapsack problem and try to find sum equal to 3, 3, 3, 3, 3, and so on, 3, and here 1, 1, 1, and so on, 1. And if this problem is solvable, so if you can find the items with some subset of items with this sum, it means that you can satisfy this Boolean formula. Well, because let's look on the solution of this knapsack problem. For this knapsack problem, you have 3 in each digit. How can you get 3 in this digit? You may take up to 2 ones here, so you must have at least one here, at least one here. So you take these two values, and you must have at least one value from here. Or you may take one from here and some two values from here, something like that. So at least one variable should satisfy each clause. For each clause, there is at least one variable which satisfies this clause. And this thing forces you to use only one variable from each group. So if you have one here, it means you can take only one of these two. It means you cannot make a variable true and false at the same time. So you just look on the solution, look at which variables you actually picked, and this gives you the solution for your free set problem. So if you can solve knapsack problem, you can give this problem to your knapsack solution and actually solve this free set problem. It means that your knapsack problem is not easier than a free set problem. And free set problem is known to be NP complete. So your problem is NP complete. That's how it's usually done. So that's how you prove that some problem is NP complete. Okay, final thing. How to prove about the first problem. So I just told that some problems are known to be NP complete, but how to prove this first problem to be NP complete? That's a different story. So for the first problem, you kind of need to actually prove that this problem is NP complete. So you need to prove that all problems can be reduced to this problem. There is some special problem, which is easier to prove that this problem is NP complete. This problem looks like this. You have some non-deterministic Turing machine. So you have some non-deterministic Turing machine. You're given this problem some input x and some time limit, some n power k. And what is the problem? So you are given this problem, this Turing machine, this input, and this time limit. Yeah, it's not exactly like this, but close enough. And in this problem, you need to check if this non-deterministic Turing machine will end on this input in this time limit. So if you make this number of operations on this Turing machine, will it eventually solve this problem for this input? Like this. This problem can be proved to be NP complete without any reducing. So you just, how to prove this problem is NP complete? You take some NP complete problem. You know that your problem is NP complete. It means your problem can be solved by some non-deterministic machine in this time. Yeah. So if your problem is NP complete, then you have some non-deterministic Turing machine which solves your problem. So you take your Turing machine, give this Turing machine to this problem. This problem will return you the result of this Turing machine. And you output the result of this Turing machine. Magic, right? So using this universal problem, you can solve any problem in NP class. You just, again, in your NP class, for any problem, there is some non-deterministic Turing machine. So you take this Turing machine, give it to this universal problem, and this universal problem solves your problem using your Turing machine. So it's obviously universal. So it's obviously NP complete, just because it can simulate any given problem. So you give it some problem, and it simulates your solution and solves your problem. So it's obviously NP complete. And now the tricky part is to reduce your problem, to reduce this problem to your problem. For example, you want to reduce this problem to free set problem. That's complicated stuff. So you kind of want to simulate the Turing machine, non-deterministic Turing machine, using free set formula. It's possible, but that's complicated. So this problem is obviously NP complete, Now to prove this free sat is incomplete, you reduce this problem to free sat. Then free sat is NP-complete. And now you reduce free sat to some of your problems and prove your problem is NP-complete and so on. So that's basically the base problem of all this NP-completeness theory. Whew. Okay, that's all for today and for this semester. See you in September.